Okay, so we'll get started, and we'll go over the first question here, and it says, a study is performed to understand the relationship between bright lights and headaches. 80 randomly selected subjects are exposed to bright lights, and 20 complain they experience headaches. 90 randomly selected subjects are exposed to less bright lights, and 12 complain about headaches. Are any conditions violated? Let me get the snipping tool. We'll say this. Okay, so we'll put that right here, and let's go over this. Okay, so we want to know, are any conditions violated? Okay, so we have a few conditions to check. So number one is, why is this not working? Okay, so is the independent and random condition met?
Yes.
And the answer to that is yes, because it says 80 randomly selected subjects, and over here we have 90 randomly selected subjects. Okay, so that is met. Okay, we want to check the next one, big population and large sample. Okay. So is big population met? Okay, so our sample size, we have two samples. Okay, N1 is 80 and N2 is 90. Okay, so our population has to be at least what? At least 10 times 80, so at least 800, and at least over here, at least 900. Okay, what would be the population that corresponds to these samples? Yeah, this is actually everybody who is exposed to bright lights or exposed to less bright lights. So anybody who might be exposed to lights. Okay, so are there more than 800 people who could be exposed to lights? Yes. Are there more than 900 people who could be exposed to less bright lights? Yes. Okay, so this condition is met. Okay, population is everyone who might be exposed to lights. Okay, and then lastly, the large sample condition. Okay, is this met? So we have two samples, sample 1 and sample 2. Sample 1 has n equal to 80 and x equal to 20. And sample 2 has n equal to 90 and x equal to 12. What the large sample condition, there's two ways to go about. One is n times p has to be bigger than or equal to 10, and n times 1 minus p has to be bigger than or equal to 10. Or the other way is at least 10 success and at least 10 failures. Okay, either method can be used to check the large sample condition. And so in this case, for sample 1, we have, quote, 20 successes. Okay, the label success is arbitrary. In this case, it would be experiencing headaches as a quote-unquote success. So how many failures do we have in this case? If I have a total of 80. 60. Okay, so 20 success and 60 failures. And over here I've got 12 successes. And how many failures would I have? 90 minus 12, 78 failures. Okay, so successes is over 10, failures is over 10, successes over here is over 10, and failures are over 10. So the large sample condition is met. Okay, so the answer to that question is all conditions are met. Let me save this. All right. Okay, are there any questions on that problem? No? Okay. We'll try this, and let me try the snipping tool. Here, we'll do 2 of these. All right, so let's do question number 2. A researcher wants to make a confidence interval for how common a certain disease is. He finds 300 randomly selected subjects and finds 2% of them have the disease. Okay, so independent, is that condition independent random?
Yes.
This one is met because it says 300 randomly selected subjects. Okay, and then we have the big population. What is a population in this case? So we have a sample of 300. So our population must be at least 3,000. At least 300 times 10, so at least 3,000. What is the population? Population is everyone, okay? Because anybody could potentially have this disease, okay? So that is over 3,000. So the big population condition is met. What about the large sample condition? Okay, so to check, we must have n times p greater than or equal to 10 and n times 1 minus p greater than or equal to 10. So in our case, we have 300 times p, which is 0.02. I get 6. And over here, I have 300 times 1 minus 0.02, so I get 294. Okay, 6 is not bigger than 10, so our large sample condition is not met. All right. Number 3. A student has to conduct a survey for a school project. He goes around the school campus and interviews people he meets. He finds data from 100 people and finds that 45 of them answered yes to his questions. Are any conditions violated? Okay. So, independent random, is that met or violated?
Violated.
Okay, yeah. It just says he goes around school campus. Okay, so this is violated. Let's check the other ones just to be sure. Okay, big population. Okay, we don't know. Okay, he finds 100 people. So the school has to have at least 1,000, and it doesn't say. So this is unknown. And large sample condition, okay, so we have 100 as our sample size, 45 success, so that means 100 minus 45, 55 failures, okay? So these are both bigger than 10, so the large sample condition is met, but again, independent random condition, that's violated, so we can at least indicate that.
Yeah.
Yes?
How about if one of the multiple choice was A and B?
Yeah, I will make sure the questions are unambiguous, okay? And if you ever feel like a question is ambiguous in the answer choices, just raise your hand and ask, and I'll clarify for you, okay? If I feel that the question you're asking is regarding the material from the class, I'll say I don't think I can answer this question. But if it's something about ambiguity or clarity, I'll be happy to clear that up. Okay. And the last one of these. Okay, so it says a company wants to survey its employees, 800 employees, decides to select 100 of the employees randomly and interviews each of them. Are any conditions violated? Okay, so here we didn't even get any other information. This one's so independent random. Whoops. What is going on here? Independent random, that one is met. Okay. Because it says randomly selected. Okay. Then we'll check big population. And this one is violated because the population is 800 employees and the sample is 100, okay? So 100 times 10 is 1,000. Our population is not bigger than 1,000, okay? So this one's violated. Okay, large sample, unknown. We don't know what our responses were. Okay. Any questions on identifying whether conditions are met or violated? Okay. Yes?
Would unknown simply be a violation?
No. And on the final exam, I'll make sure none of these are unknown. Okay. In this practice final, some of the conditions were left unknown, but in the actual final, none of the conditions will be unknown. And if you feel like something is unknown, just raise your hand, and I'll be happy to answer. Okay. Yes.
So I understand about the random, but could it ever just be that the independent is violated?
On rare occasion, we didn't really cover very many examples like that. For example, somebody could say, I'm going to flip a coin, and if it goes heads, I'm going to select all the men in the classroom, and if it lands tails, I'll select all the women in the classroom. Technically, that is a random selection procedure, but because I'm selecting not one by one, but everybody, the group at a time, it's not independent. You don't have very many sampling methods like that that are commonly used. Okay. All right, so don't worry about that. But they are grouped together when we teach. So, yes.
So on the test, because it's multiple choice, it'll ask which of them are violated.
Mm-hmm.
That's what we can expect, like a specific question.
Yeah, it'll be very similar to what you saw here, okay? Which says, which will list off a scenario just like you see, and then it will say, ask which condition is violated. So it'll be very similar to what we've done. All right, so we'll do this first question. A farm wants to test 2 different diets for their cows to see which diet causes more weight gain, okay? They randomly select 10 cows to give diet 1, and they select 12 cows for diet 2. After two weeks on diet 1, the 10 cows gained an average of 15.2 pounds with a standard deviation of 4.1. After 2 weeks on diet 2, the 12 cows gained an average of 12.6 with a standard deviation of 3.4. The following questions refer to a 95% confidence interval for the difference in average weight gain, diet 1 minus diet 2. Okay, so I've been trying to emphasize that the most important thing, the most important step in any of these questions is figuring out whether you are dealing with means or proportions, and whether you have one sample or two samples, and whether or not you're doing a confidence interval or hypothesis test. Okay, that's the most important step. Okay, on the quizzes that I graded last week, or that you guys did last week, a lot of people I noticed were getting mixed up. They thought they were doing proportions when it was dealing with means, or vice versa, or things like that. Okay, so in this case, do we have proportions or means? Means. And how do we know? Okay, we see words like average. Okay, so that means we are dealing with means. Okay, do we have one sample or two samples? Two samples, right? We see 10 cows from diet 1 and 12 cows for diet 2. So we have two samples. Confidence interval or hypothesis test? Okay, very clearly it says confidence interval. So this is the most important step. Confidence interval. As this will guide how you do the rest of your problem. If you mess this up, the rest of your problem is going to be messed up. Okay? Alright, so now that we figured that out, we can start answering our questions. For a 95% confidence interval, what will be the center of the interval? Okay? Well, when we have two samples and it's dealing with means, the center of our confidence interval is x bar 1 minus x bar 2. Okay? That's listed in our study guide if you aren't sure. Okay, it says what's the center for two sample means? It's the difference x bar 1 minus x bar 2. Okay, so again, you must know that you're dealing with two samples means. Okay, so we've got x bar 1 minus x bar 2. Okay, so at this point, let's go through our problem, circle our numbers, and label what they are. So 10 cows, this is going to be what? N1. 12 cows, N2. All right, then still that we have the same 10 cows. 15.2 pounds, that is x bar 1. 4.1 pounds with a standard deviation, this is S1. Okay, so I'm going to just list off. N1 is 10, x bar 1 is 15.2, S1 is 4.1. All right, N2 we have 12. And then 12.6 pounds, that's going to be our x bar 2. And S2 is this number right here, 3.4. Okay, so number 5, we do x bar 1 minus x bar 2, which gives me 15.2 minus 12.6. The center of my interval is going to be 2.6. For a 95% confidence interval, number 6, what value will you use for T star? Okay? T star requires that we have our degrees of freedom. So what is our degrees of freedom? Degrees of freedom is n minus 1, and which n do I use? The smaller one, so I'm going to use the 10. So I'm going to have degrees of freedom equal to 10 minus 1. I have 9 degrees of freedom. Okay, so I have 9 degrees of freedom. What is the confidence level? 95%. So I'm going to go to my reference table. And I'm going to say 9 degrees of freedom, 95% confidence. The number I'm using, 2.262. Okay, and again, if you weren't sure about that, you can always go to the study guide where it says what's the critical value, and it says T star comes from the T table and degrees of freedom is n minus 1. Use the smaller n. Oh, standard error. For two sample means the standard error is S1 squared over N1 plus S2 squared over N2. Okay, so here it says, the next part says, what's the standard error? The standard error, S1 squared over N1 plus S2 squared over N2. So we're going to use these numbers that we have over here. 4.1 squared over N1, which is 10, plus S2 squared, 3.4 squared, over N2, which is 12. Okay? I think some of you guys have issues with using your calculator, but let me, so I'm going to show you exactly what buttons I'm pushing here. I'm going to type in 4.1 square button divided by 10, so that's this first number. And this calculator is smart enough to understand order of operations, so I can just go to the next one. 3.4 square button divided by 12. Okay, so that covers everything that's on the inside, and I'm going to hit enter. So that gives me 2.644. That's not my answer. I have to take the square root of that. So I'm going to hit the square root button and then the answer button. So I get 1.626. That's the answer that I get here. Okay, that's my standard error. 1.626. Okay. So number 8 says, create a 95% confidence interval. So at this point, I'm just putting everything together. So I'm going to put x bar 1 minus x bar 2 plus or minus t star times the standard error. So that gives me 2.6 plus or minus the t star, which is 2.262, times 1.626. Okay, so I have 2.6 plus or minus, let me just do this, times 2.262. So I get 2.6 plus or minus 3.678. So when I punch that out, that gives me 2.6 minus 3.678. I get negative 1.078 to 2.6 plus 3.678 gives me 6.278. So this is my confidence interval. Is everything so far so good? All right, so let's look at number 9. Based on your 95% confidence interval, do you conclude that there is a difference in the average weight gain? So how do we answer this question? Okay. Well, again, if you're not sure, you can always go to the study guide. It says, what conclusion or decision can be made on the confidence interval? Okay. It says, for two sample means, the question might ask if there's evidence that the means are different. In this case, you will look to see if 0 is in the interval or not. If 0 is in the interval, there isn't evidence that the means are different. That's what it says. Okay, 0 is in our interval because it goes from -1 to +6. So we're going to say 0 is in the interval. And again, what did the study guide say? It says, if 0 is in the interval, there is no evidence that the means are different. And lastly, number 10, if we had made a 90% confidence interval, how would it compare to your 95% confidence interval? What would happen? Yeah, the only thing that would change is my choice of t star. Okay, so only t star would change. And the t star that we would use would go from 95% to 90%. and we see that that number is smaller. So that means our interval becomes more narrow. And there you have it. Okay. Questions? Feeling good? Go back? Sure. Oops, that's not. It's from the other class. Okay, we'll go on to the next question. Ruler and yardstick factory. It's my favorite question. Not really. Okay. We'll see if this shows up on my final defense here. Ruler and yardstick factory. A machine is suspected to be defective. Yardsticks it produces are supposed to be 3 feet long, and you measure a random sample of 40 yardsticks and you find that the average length is 3.02 feet with a standard deviation of 0.03. Is this evidence that the machine is producing yardsticks that are too long? Okay, one-sided or two-sided test, etc., etc., etc. Okay, well, first off, what's the very first thing we have to do? We have to decide if we have one sample or two samples, are we dealing with means or proportions? So what are we dealing with? Means or proportions? Okay, so it says we're looking at the average length, okay, and we also see standard deviation. So the standard deviation with a number only appears if we are dealing with means. Okay, so we've got means, and how many samples? 1 or 2? Only one sample. One sample of 40 yardsticks. That's it. Okay, so we're dealing one sample means, and then are we dealing with a confidence interval or a hypothesis test? Okay, so let's just quickly scan through these questions. And we see things like, what would your hypotheses be? Okay, so well, that makes it easy. Now we're dealing with a hypothesis test. Okay, well, let's list off the data that we have. Okay, we have an n. What is our n? 40. We have an x bar, and what is that? 3.02. We have an s, 0.03. And for our hypotheses, we need an H0. Or, I'm sorry, not an H0, a mu0. What is our mu0? 3, because it's supposed to be yardsticks that are exactly 3 feet long. Okay. Now, the question asks, is this evidence that the machine is producing yardsticks that are too long? So that's going to be our hint to our first question, number 11. Is this a one-sided or a two-sided test? One-sided test, okay? Because we're asking if they're too long. So words like too long, too short, more, less, those types of things are one-sided. Two-sided tests use words like, are they different? Has it changed? Things that don't imply whether one thing is expected to be bigger than the other. Okay, so this is a one-sided test. So, number 12 says, what would the hypotheses be? So we have a null hypothesis and an alternative hypothesis. The null hypothesis states that mu is equal to 3. And the alternative will be mu is greater than 3 because it says, is it too long? Too long, greater than 3. Okay. Now, on the quiz, I noticed some of you guys wrote stuff like this. All right, this is not correct, okay? It's not that H0 is equal to 3. It's that the null hypothesis states that mu is equal to 3, okay? So this is wrong. Don't do that.
But we won't really have to do multiple choice, right?
Oh yeah, you won't even have that option, okay?
Problem solved.
Problem solved, okay? And make sure, don't use x bar, okay? We're talking about mu. Don't use p, because we're dealing with means and not proportions. All of these things, okay? Null hypothesis always has an equal sign. Again, if you're not sure, you can always check with the study guide. And it says, what would the hypotheses be? And it says, mu is equal to this versus mu isn't, and might be greater than, smaller than, less than. Okay. Fine. What is the value of the test statistic? Okay, so our test statistic if we're going to follow the study guide, it says observed minus null divided by standard error. Okay, so for one sample mean, the observed value is x bar. So we're going to do x bar minus what's in the null, which is 3, divided by the standard error. Okay, so our standard error we have to calculate. And if you can't remember, you can always check here. Standard error is, for one sample mean, s over the square root of n. So our standard error is s over the square root of n. Okay? So now we have everything that we need to get our test statistic. Okay? Standard error is s over the square root of n, so I'm going to do 0.03 divided by the square root of 40. That gives me a very small number, which is 0.00474. And so my test statistic is going to be x bar 3.02 minus 3 divided by, and actually let me just add on a few more decimals here, divided by 0.0047434. Okay? And if you keep all of those decimals, your test statistic ends up being 4.216. So that is our test statistic, 4.216. Let's find the p-value. Okay, so to get the p-value, we're going to look up our test statistic, 4.216, in our t-table. So we've got to figure out our degrees of freedom. So how many degrees of freedom do I have? 39 degrees of freedom, right? Degrees of freedom is n minus 1. So I have 39 degrees of freedom. If I go to my reference table, the t-table, I don't have 39 degrees of freedom. So what do? I always round down. So 39 is closer to 40, but always round down. We're going to use 30 degrees of freedom. Okay? And I'm going to see where in this row, for 30 degrees of freedom, where does the number 4.216 fit? Okay? Well, 4.216 goes all the way over here. 4.216 is bigger than 3.384. So that means what? The tail area that I have is going to be more or less than 0.001. Less. Okay, so the p-value, so my tail area is less than 0.001. Okay? Now, again, on the quiz, I think some of you guys have your less than greater than signs mixed up. So if you just remember from school, like You have the alligator, right? That's gonna eat the thing. He's hungry, so he always wants the bigger one. So, which side do we get? Okay, so 0.001 is bigger than what our tail is what we're saying here. Okay, so when it comes to our p-value, do I need to double it or do I leave it? It's one-sided, so I'm going to just leave it. Okay. So the p-value is less than 0.001. I know it's silly, but there were enough of you who made a mistake with the way the less than greater than should be pointed that I feel like it's worth bringing up. Okay, if alpha is 0.05, what is our conclusion? Is my p-value bigger or smaller than alpha? My p-value is smaller than alpha, so my decision is what? Reject what? The null hypothesis. Okay? And that means, is this evidence that the machine is producing yardsticks that are too long? I've rejected the null hypothesis. The null hypothesis says that they're equal to 3. I'm rejecting that. So I come to the conclusion that mu is greater than 3. So we say we have evidence that mu is greater than 3, or the machine makes yardsticks that are too long. Yes?
I'm just number 14.
Mm-hmm.
I'm not getting that.
Not getting number 14. So our test statistic is 4.216, right? For number 13.
Yeah. I got
Okay.
that.
So I'm going to look up that test statistic in the table.
Yeah, I got that.
Okay. And so 4.216 is bigger than 3.384, which means the value for my tail is going to be beyond what's in the table over here. So as I get further away from 0, the amount in my tail gets smaller. So the amount in my tail is less than 0.001. Is that part okay?
Yep.
Okay, so that's all I've written down here, is that my tail is smaller than 0.001. Okay, and because it's a one-sided test, my tail is my p-value. So here I'm just writing my p-value is smaller.
P-value.
Huh?
So that is the p-value.
That is my p-value.
That's the part I was like not connecting. All right.
Okay, that's it. Okay. And so now that our p-value is small, we reject the null and we say we have evidence that mu is greater than 3. We have evidence for the alternative, and the machine makes yardsticks that are too long.
So essentially, the p-value is 0.001?
The p-value is less than 0.001, but yeah, you can just treat it as 0.001. Okay? All right, number 16. If this conclusion that we made was wrong, what kind of mistake did we make? So it's either going to be a type 1 or type 2 error. And it's a type 1 error. Type 1 is our decision is to reject, but that was a mistake. And that's if it says if our conclusion here to reject was a mistake, what kind of error was that? That's a type 1 error. So that just requires knowing your definition of type 1 and type 2 error. Yes?
If this was a two-sided,
Mm-hmm.
and your p-value started there at .001 and you doubled it,
Yes.
would you then write p is less than 0.001 or P is less than 0.002?
Yeah, so if it's a two-sided test, you would double your p-value and you would write p-value is less than 0.002. Okay, everyone got that down? If we had a two-sided test rather than a one-sided test, I would take my p-value and I would double that. And so I would write my p-value is less than 0.002.
So basically times it by 2?
Yes. If I had a two-sided test. Yes.
And then into 15, the 0.05, like how is that connecting that?
So we are comparing our p-value, which we're going to just treat as 0.001.
Yeah,
Is 0.001 bigger or smaller than 0.05?
it's less.
It's smaller, so that's what we have. Our p-value is less than alpha, and if the p-value is less than alpha, that always means we reject the null.
And then it's just type 1 error.
And then,
So it'd be, okay.
yeah,
Got it.
got it, great.
It's easy.
Yeah, you're in.
So, and you know it's type 1 is if you reject the null?
The type 1 error, okay, so first of all, rejecting the null is not necessarily a mistake. But if you reject the null and it is a mistake, then it's a type 1 error. Okay? So type 1 error can only happen if you reject the null. And a type 2 error can only happen if you don't reject the null. Okay? Type 1 is rejecting the null, but that was a mistake. Type 2 is you didn't reject the null, and that was a mistake. Okay? Okay. You can think of it as if you think of your, I don't know, past love life, if there is such a thing. No, I don't. That's not an insult here. Okay. So a type 1 error would be rejecting, dumping someone, and then you regret that decision. Okay. Now, you hope that doesn't happen. You don't want to make these types of mistakes. But type 1 would be rejecting someone, and then that turned out to be a mistake. The person, I don't know, someone, you dump someone and then they go on and become a rock star, that could happen. But type 2 is not rejecting someone, but maybe you should have. So that's, those are people who are stuck in relationships that, well, maybe, whatever. Okay, anyway. So just think of that, okay? If it helps you remember what's a type 1 and type 2 error. Ideally, neither of those situations happen, right? You reject people that you're not supposed to be with, and you don't reject the one that you're supposed to be with. So, we'll go on, because we love this. (17-22). Researchers believe that 14% of the population is left-handed. A local school district decides to see if their students have a different proportion of left-handed people. The school has a total of 1,500 students, and they randomly select 90 students for the study. They find that 15 of them are left-handed. Is this evidence that the proportion of left-handed students at the school is different from the population proportion? All right. One sample, two samples, means or proportions. That's what we got to figure out first. Always. Okay, so we have proportions, because it says proportion right here. Also, because we're dealing with whether a student is left-handed or not. That's a categorical variable, so anytime you have a categorical variable, it's proportions. One sample or two samples? Just one, right? 90 students. One sample. Confidence interval or a hypothesis test? Well, we look through the questions and we see things like make a confidence interval, so that makes it easy. All right, so let's look at what we have for our numbers. What is our sample size n? 90, okay? And how many are left-handed? X is 15, okay? So number 17 asks, what is our sample proportion? That is p hat, and that's going to be 15 over 90. I have 0.1667. Okay, 90% confidence interval. What critical value z star would you use? Okay, yeah, this comes from our just the numbers that we need to know because it's for proportions. So when you have different things, you have different things to do. So proportions, 90% confidence interval says we use 1.645. So z star (1.645). Confidence interval, what is the standard error? Standard error, p hat times 1 minus p hat over n. Okay. Also, this is in our study guide right here. P hat 1 minus p hat over n for the standard error for one sample proportion. So I take the square root of 0.1667 times 1 minus 0.1667 over n, which is 90. And when I do that math, I get 0.0393. Do I need to do that on the calculator, or are you guys good? We're good, right? Okay, what will the center of the interval be when making a confidence interval? What do we put in the center of our interval? P hat. P hat. So the center is going to be 1.667. Okay, if you weren't sure, you can always look at the study guide center. It says for one sample proportion, it's the sample proportion, the p hat. All right, make the 90% confidence interval. So we're going to go p hat plus or minus z star times the standard error. So that gives me 0.1667 plus or minus 1.645 times 0.0393. Okay, that when I go through all of that, I get 0.1021 on the small side all the way up to 0.2313. Okay, again, that's just a matter of punching things into your calculator. So 22 asks, based on this interval, is this evidence that the proportion at the school is different from the nation? What is the national proportion? 14%. Okay, so nation is 14%. And the question is 14% within our interval? Yes. So 0.14 is within our interval. Which goes from 0.1023 or 1021 to 0.2313. So does that mean it's different or not different? Yeah. So our, or I should say, so we do not have evidence that it's different. How's that? Okay, can I go on? All right. Where is this? Number 23 through 27. Okay, it says you buy a bag of Starburst candies and a bag of Jolly Ranchers, and the Starburst contain 80 pieces and 12 of them are cherry flavored. The bag of Jolly Ranchers contains 70 pieces and 14 of them are cherry flavored. Assuming these are truly random assortments, does this provide evidence that Starburst and Jolly Ranchers have a different proportion of cherry flavored candies? And so we'll say group 1 is the Starburst with 80 pieces total and 12 cherry candies. Jolly Ranchers 70 pieces total, 14 cherry candies. Perform a hypothesis test, 5% significance level. Okay. Are we dealing with means or proportions? Proportions, right? Because we're dealing with a categorical variable. Is the candy cherry flavored or not? It also says proportion right here in the question. Do we have one sample or two samples? Two samples. I've got Jolly Ranchers and Starburst candies. Okay, and we are dealing with a hypothesis test. Okay, so let's identify our data. So we have sample 1, which will be our Starburst candies. So we have n equal to 80 and x1 equal to 12, which makes p hat 1, 12 over 80, 15%. Sample 2 will be the Jolly Rancher candies. N2 is 70, x2 14, and p hat 2 will be 14 over 70, 20%, 0.2. All right, so 23 says write the appropriate hypotheses. So what are the hypotheses? We've got null hypothesis and an alternative hypothesis. Okay. Again, if you're not sure, you can always go to the study guide. I'm just trying to get you to see that I'm trying to help you. All right. For two sample proportions, the null is P1 minus P2 equal to 0, and the alternative is P1 minus P2 not equal to 0 or greater than or less than. Okay. So that's what we're doing. So the null is P1 minus P2 equal to 0 versus P1 minus P2. Do I use greater than, less than, or not equal?
Not equal.
Not equal. Because it says, is it different? Which means we have a two-sided test, right? Notice I'm using P, not P hat, not mu, okay? Again, just follow what's written in the study guide. This is correct here, okay? For two samples proportion, do this. There's no second guessing. All you got to do is follow the steps, follow the directions. You got to think, of course. Identify.
That could also be P1 equal to P2.
It could also be P1 equal to P2. P1 equal to P2 also completely allowed. All right, again, on the multiple choice section, you might see this, you might see this. Be prepared for either. What is the value of P hat? What do we do with P hat? We're going to do x1 plus x2 over n1 plus n2. So I have 12 plus 14 over 80 plus 70. I have 26 over 150. .1733333. Let's make our test statistics. Yes?
How many decimal points do you want to see?
It doesn't matter. It's going to be multiple choice, so keep enough so your answer matches. When I make the multiple choice, I don't do any rounding. I actually leave all the answers in the calculator itself. So the more you keep, the closer your numbers will match mine. Okay. So for our test statistic, we're going to first have to calculate the standard error, and then we can get the test statistic, because the test statistic is p hat 1 minus p hat 2 over the standard error. This is our test statistic, but we got to do the standard error first, which is going to be p hat times 1 minus p hat times 1 over n1 plus 1 over n2. So if we plug in numbers here, 0.1733 times 1 minus 0.1733 times 1 over 70, or I'm sorry, 1 over 80 plus 1 over 70. All right, do you want me to punch this into the calculator and show you how to do this? All right, well actually, so because I did 26 divided by 150, this number is right here in the screen, so I can just reference that using the answer key. So I'm going to do answer times parentheses 1 minus that times parentheses 1 over 80 and 1 over 70. 1 divided by 70. Close parentheses. I hit enter. This is what I get on the inside. I'm going to have to take the square root of that. And so I get 0.06195. Okay. So Z is P1 hat minus P2 hat over the standard error. So P1 hat we found was 0.15 minus P2 hat, which is 0.20, divided by the standard error, 0.06195. I punched that out. I put this into the calculator. So I'm going to do parentheses, 0.15 minus 0.2 divided by the answer key. All right. I get negative 0.0807. Okay. So that is my test statistic, number 25. Test statistic, negative 0.807. What is the p-value? 26. So with my test statistic, what do? I go to my table. And which table do I go to? The Z table. Anytime I'm dealing with proportions, I always go to the Z table. Z table for proportions, always. Okay? Now, my test statistic is negative 0.807, so I'm going to have to look up what? Z equal to negative 0.81. Okay? Alright, so we go to the table. We go to Z equal to negative 0.81. Let's see. Negative 0.8 and the column 0.01, 0.2090. Okay, so from the table, the area to the left is 0.2090. Okay, so now we have questions. Do we take 0.2090? Is that my answer? Do I double that? Do I do 1 minus that? Do I double that? What do we do? Okay, let's draw a picture. Okay, so what I looked up was negative 0.81. And I took the area to the left, and this area is 0.2090. Now it says, does this provide evidence that Starburst and Jolly Ranchers have a different proportion? Okay, so different means I'm going to take my tail area and double it. Okay, so in this case, 0.2090 is my tail area. Okay, so if we had a different picture, the tail area might be what's to the right. But if you draw the picture, the tail is always the side that doesn't have the hill. Okay, if it has the hill, it's not the tail. Okay, so whenever you draw a line, right, you're either going to have the little wedge piece or the part with the hill. Okay, so we have the wedge piece, so that is our tail. And for a two-sided test, we double the tail. So my p-value will equal what? 2 times 0.2090. So my p-value is equal to 0.4180. Does that make sense? Is everyone okay with that? Yes, no, not so much? Okay, so again, you're always asking what is in the tail. Okay, so when you have a two-sided test, okay, two-sided test means we double the tail. Okay, let me just do a quick aside. So if, let's say we did our test and we happen to get
The one you did before, that was a one-sided.
yeah, one-sided, okay, but it was a t-table, so it's always going to give you the tail. Okay, this thing really you only have to worry about when you have a z. Okay, so let's say our z-score ends up being positive 1.3 or something like that. Okay, remember the table always gives you the area to the left, so when you look up positive 1.3, the area that you get to the left is going to look like this. Is this the tail or not? This is not the tail. So if you want the tail, you'd have to take this and you'd have to subtract 1 from it so you can get the area to the right, and then that would be the tail. Okay, so whatever's in the z table, you would subtract from 1 to get the tail, and then if it was two-sided, then you would double the tail. So you always first have to figure out the tail, whether you have the tail or not the tail, and then you would subtract from 1 or double it. Okay, the tail is always going to be less than 1/2. Okay, so if you ever get a number that's bigger than 1/2 as you're working, you know that's not the tail. The tail will always be less than 1/2. So that's another way to check whether you've got the tail or not. All right, 27. What conclusion do we make? Our p-value is 0.4180. So what do we decide? Reject or no? Do not reject. Okay, do not reject. So alpha is not provided. Oh, no, it does. It says perform a hypothesis test at 0.05. So do not reject the null because our p-value is bigger than alpha. And what does that mean? We do not have evidence that the proportion of cherry candies is different. How's that? Okay, I'm going to pause.